So, how big is the universe? We currently know that the observable universe is a bubble with a diameter of around 92 billion light-years. Wow, that's really big. But what about the entire universe? How big is it? Does it stop there, on the observable universe, or does it go beyond? How much further? Stay with us for the next few minutes while we try to find an answer. So, to better understand the current perspective on the vastness of our universe, we first have to understand a few concepts. Let's start with the observable universe. This is the limit of how far we can currently see into the distant universe. And what does that really mean? Well, when you look at the stars, what you're actually looking is into the past. Yep, that's like having an actually time machine right in front of your eyes. Why? Well, because light travels at around 300,000 kilometers per second, which seems really, really fast. But on the scale of the universe, well, it's kind of slow. So when you're taking a bath sun, you're actually catching light that left the sun 8 minutes ago. So the sun could actually disappear, and you're just going to notice it 8 minutes later, when you might start to feel a little bit chilly. But let's return to the observable universe. When you look at the night sky, you are actually seeing the past, because light takes time to reach our eyes. As we mentioned before, light from the sun takes about 8 minutes to reach us, but it can take much, much longer from distant objects. So when you look at the night sky, you're essentially peeking into the far past. It's like flipping through a history book that stretches back centuries, millennia, and far, far more. But there's also a cosmic horizon, much like the ocean's horizon, that marks the edge of our observable universe and limits how far we can see. This horizon is determined by the universe's age, about 14 billion years. However, because the universe was and is expanding, we are now seeing stuff that are 46 billion light-years away from us. That's around 92 billion light-years in diameter. We've made a video on this in more detail if you want to check it out. But wait, is the universe stretching out? Indeed, the universe is stretching out all the time, and it seems that's not doing it at the same rate everywhere. This is mostly thanks to dark energy, a mysterious force that's pushing things apart faster and faster. It's like throwing a ball up in the air, but instead of coming back down, it just keeps going faster and faster into the sky. But returning to the concept of observable universe, think of it as a bubble with Earth at its center. That is around 92 billion light-years in diameter. This is the farthest we can currently see. However, there's no reason to believe that the universe should actually stop there. Beyond this visible limit, the universe likely continues into regions we still haven't detected because, for now, we have no way of seeing anything beyond the reach of the light, since the light from those spaces still didn't have time to travel to us since the universe began. And perhaps we never will, as the universe is continuously expanding. This limit constrains our view to just a portion of the universe, leaving everything that is outside this bubble unobserved and mysterious. But how vast might it be outside this bubble? Well, to better understand the size of all the universe and how big it is, it's also important to understand its shape. Why? Because knowing the shape can help us estimate the universe's true size. For example, more than 2,000 years ago, we also tried to determine how big something could really be. In this case, the Earth. Eratosthenes, who became the chief librarian at the Library of Alexandria that already suspected that Earth was spherical, used some simple observations involving sticks, shadows, and maths to figure out how big our planet really is. And he did it with incredible precision even before fancy technology came along. In recent years, scientists come up also with some really clever ways to try and determine the shape of the universe, and by doing so, estimate its size. So they tried to find objects really far away in space whose sizes were already known, and then measured how big these objects appeared from here. How they knew the size is probably a topic for another video. If these objects appear the size they were expected to be, then the universe is flat. If they look larger than expected, it suggests that the universe is closed, wrapping around itself like a sphere. And finally, if they appear smaller, It indicates that the universe is open, kind of like a saddle. Let's go a bit deeper to understand how they can infer that and what the implications are. First, let's consider a flat universe, the simplest model where space is not curved. In a flat universe, parallel lines stay parallel indefinitely, and the angles of a triangle always add up to 180 degrees. This flat shape aligns with our everyday experience and suggests an infinite expanse, where the universe would continue forever without looping back on itself. So if you try to measure something that is far away, and that you know beforehand how much it measures, the result should be identical. That's what we are used to, so it's very straightforward. If you know it measures 1, then when we measure it from far away, it should still appear to us like 1. But the universe could have a closed shape, like the surface of a sphere. In this model, if you travel far enough in one direction, you would eventually return to your starting point. Parallel lines converge, and the angles of a triangle add up to more than 180 degrees. This type of universe is finite but unbounded, with no edges but a contained volume. In this case, an object that's further away should appear to us bigger than its actual size, due to the curvature of space. This concept can be challenging to understand with our intuitive perception of reality, but because space itself is curved, something that we know that measures 1 can show to us, like having, for example, a measurement of 2. By measuring this curvature of the universe, scientists could potentially infer its size. Finally, we have the hyperbolical model that resembles a saddle shape and is commonly referred to as the open universe. Here, parallel lines diverge, and triangles have angles that add up to less than 180 degrees. This shape probably implies an infinite universe that expands forever, like the flat model, but with a different geometry. In this case, if you try to measure something that is far away whose size you already know, the result should appear smaller than it actually is. Much like the previous example, this is definitely contra-intuitive, and it's not easy to visualize something like that. Anyway, imagine, for instance, knowing that an object far away measures 1, it would appear to us smaller than that, like, for example, 0.5. And what were the results? After analyzing all the data concerning the curvature of the universe, scientists concluded that it is most likely flat and probably infinite. However, no measurement is perfect. Although the universe may seem flat to us due to its vastness, it could actually be curved. But since the deviation is so small, we can't determine whether it is flat or curved due to the margin of error of our current instruments. Imagine this. You're on top of an incredibly large sphere, 1 billion times larger than Earth, and you are very, very tiny. You're trying to determine if you're standing on a flat surface or a curved one. Since the sphere is so huge and the curvature is so unbelievably small. Without highly precise instruments, you might be led to believe that you are on a flat surface. So, they have considered what range of universe sizes would still align with our measurement uncertainties, and came up with this. They determined that the largest possible universe consistent with our observations could be infinite, and the smallest would be 250 times the size of the observable universe, which would still be an incredibly huge and big universe, but still finite. To put some numbers on this, the observable universe is around 92 billion light-years, which we have to multiply by 250, and the result is 23,000 billion light-years. That's a whopping 2.17 times 10 to the power of 26 kilometers, or 1.35 times 10 to the power of 26 miles. That's 217 septillion kilometers in the short system. That's 217 followed by 24 zeros. Or 135 septillion miles in the short system. That's 135 followed by 24 zeros. That's really hard to grasp how big that could actually be. But to try and visualize it better, imagine Earth shrunk down to the size of an atom, while the entire universe shrunks to the scale of our planetary solar system. That's the staggering relation in scale between Earth and the universe, a mere atom among our planetary solar system. Or here's another way to see it. Hold a billiard cue ball in your hand, that's Earth, and then think of the entire Milky Way galaxy as the universe. That's the immense scale and proportion we're talking here. It truly puts things into perspective. Now, that's just the smallest size we think the universe can be, but it could be infinite for all we know. But that's not all. There's a theory called inflation, suggesting that in the early universe, space underwent exponential expansion. According to that theory, the universe could be a staggering 10 to the power of 23 times bigger than what we currently can see in the observable universe. So, you take the already enormous size of the observable universe and multiply it by a number with 23 zeros. What? Yes, that's right. Multiply 870 sextillion kilometers, or 540 sextillion miles, which is roughly the diameter of the observable universe, by 10 to the power of 23. To put it in perspective, if the visible universe is around 92 billion light-years across, this theory says the whole universe could be around 9.2 times 10 to the power of 33 light-years across. That's a whopping 8.7 times 10 to the power of 46 kilometers. That's 87 quatuordecillion kilometers in the short system. That's 87 followed by 45 zeros. To miles, that's 5.4 times 10 to the power of 46. That's 54 quatuordecillion miles in the short system. That's 54 followed by 45 zeros. Herf, that's incredibly, unbelievably huge. But as of now, we don't actually have data that can definitively support this 100%. So the final answer to how big the universe truly is that we don't really know. So it's possible that the universe is infinite, but if it is not infinite, then it should be at least 250 times bigger than the currently observable universe. That's a bubble with a diameter of around 217 septillion kilometers, or 135 septillion miles, and expanding. Wow! If you liked this video and want to explore the possibility of infinite versions of yourself, click on this video. Or if you want to see another one of our videos, you can click on this one. Thanks for watching.